Okay, guys, so just a little bit more about our binomial distribution. So, looking at mean, standard deviation, we'll start with taking a look at explaining its distribution. So, we describe its distribution just like we do any other, looking at the shape, the center, and the spread. So, consider that family of 5 and looking for the number of children with type O blood. So, looking at the graph that we have here, we see that the probability distribution is skewed to the right. It's going to be more likely that 0, 1, or 2 children would have type O blood than 3, 4, or 5 children. Okay, the center, well, our median is based at 1. If we use the formula for our mean, we would find that it would be 1.25. Okay. 0 times is our expected value, adding them all together. Okay, our variance given our formula for a random variable, FYI, your expected value and your variance are all formulas that are given to you. You can also find them in your calculator by doing one list for your random variables and your next list being your frequency list, which is your probabilities, and going to one variable stats. And your variance would be 0.9375 using formula or the calculator. Square root of that, your standard deviation, the calculator would actually just give you that 0.968. Okay. So let's think about why the mean might be 1.25. So because each child has a 0.25 chance of inheriting type O blood, we'd expect 1/4 of the children to have this type of blood. So in other words, the mean of x would be 5 times 0.25. So it would be 1.25. So this method can be used to find the mean of any binomial random variable with parameters n and p. So that's going to give you the number of trials times your probability. Number of fixed trials times your probability. And then it would show that your standard deviation is going to be the square root of your mean times 1 minus your probability. So that's the probability of a fail. So number of trials times the probability of success times the probability of a fail, and it's the square root of that. So remember that these formulas work only, though, for binomial distributions. They can't be used for any other kind of distributions. Okay, so going back to that taste test that we did. So let's say that Mr. Bullard's AP statistics class did that same activity that we did in class last week. So if we assume that the students in his class cannot tell tap water from bottled water, then each has a 1/3 chance of correctly identifying the different type of water by guessing. So we'll find the mean and standard deviation of x and we'll interpret it. Before we do that, though, let's first explain why we know that x is a binomial random variable. So, I guess we have to go through. We can go through our bins, right? So it's binary because on each trial you can have a success, which is the correct identification, and a failure, which would be the incorrect identification. It's independent because one student's result would show nothing about what another student's going to guess. And the number would be 21 trials. There's 21 kids in class. It's a set. You can't go past that. And then the success, each student had a 1/3 chance of guessing correctly, and that doesn't change throughout. So because x is counting the number of successes in its binomial setting, it would be a binomial random variable. So because of that, we can now use those formulas for finding the mean and the standard deviation. So the mean is going to be found by taking the number of trials, multiplying it by the probability of a success. So it would be 7 in this situation. So in other words, we'd expect about 7 to guess correctly. And the standard deviation found by the number of trials times the probability of success times the probability of a fail, taking the square root of that, it's going to get us about 2.16, which means if the activity were repeated many times with the groups of 21 students guessing, the number of correct identifications would differ or vary from the mean by about 2.16. Okay, I'm going to actually go